So this is a simple problem to solve for internal loadings in a beam. And it's simple, this problem, because it has a free end as we are seeing here, as opposed to have two ends with supports. And the problem is asking to find the internal loadings. We didn't do this in the class of statics, but we do this in the class of mechanics of materials many times in almost all problems. So we look for internal loadings at different points, and this is one point in case for where we can see that we make a cross section AA, and it's easy for us to take the right side of that cross section when we solve, because it gives us less work to do as opposed to selecting the left side. In that case, we see the left side has a support, and we first have to find the reactions of that support and then come back and solve for the reactions, internal reactions in point A. So let's do the free body diagram, and I highly recommend to not skip this step because this is where errors are coming into the problems. And for the right side of this point, this cross section AA, we can see here that we have that external loading of 300 pounds, and then the problem says that this boom DF of this jib crane has a uniform weight of 50 pounds, as we expect many things to have be like that, especially if they are like this one, apparently heavy. We are putting a uniformly distributed load like a rectangle that we can see here along these 3 feet where we have it there. And of course, we need to calculate the reaction, the resultant. As you recall, we did that in statics. So we have 50 pounds per foot multiplied with 3 feet of length. We get 150 pounds. And we put that reaction at the middle of this width of 3 feet. Where we expect at 1.5 feet to be the centroid for that resultant to act. And then we have the internal reactions, because we can see here, because this is a continuous beam, it's part of a beam. We expect to have at the right point side, which is connected with the left side, in a fixed way. So we expect 3 internal reactions, force along the x-axis, a force another one along the y-axis, and another constraint, which is the moment which constrains the rotation around that point A. So at this moment, the free body diagram is already done, and we can go to the next step to use Newton's second laws. We can write 3 equations here to solve for this on, and it's when we look at along the x-axis, it's obvious by observation there is no reaction there, because there is no force acting along the x-axis. I still wrote this Newton's second law there for you to see how we use it. And then along the y-axis, we have this AY. If we take it positive upward, then we have to subtract that 300 pounds, and we also have to subtract that 150 pounds there, because they all act downward. And when we do the math, very simple, we can calculate AY is equal with 450 pounds. Now, for the moment, we can write the equation. One of the simplest ways to write it right here at point A. And if we take the counterclockwise, as again, it's up to you how you take it. I selected here counterclockwise. So now there's a positive. So now we have that moment MA, which is our unknown. And we have to have this force that pulls downward, as you can see. And because it does that, it will rotate this whole beam, this segment of the beam around that point A in a clockwise direction, which in that case will be negative for us. So we subtract it 300 pounds times the force arm, which is 3 feet. Then we have the other force of 150, again is pulling downward, and it tends to rotate the beam, this beam segment in a clockwise direction, again negative with our selected positive direction. So, and the moment arm will be, the force arm will be 1.5 feet. Again, very simple. We can calculate the moment at point A when we solve for it. And the next problem will be a little bit more complicated because we'll tackle a beam that has two supports basically at each end. So that point A will be between the two supports. Hope you have a beautiful day, and let me know if you have questions, still have questions about this.